Okay, so my previous uh, recording of this got botched, so I'm going to talk over what I did for this practice exam 3. Um, and hopefully we're not going to have the same issues with like frame rate dropping. That was what happened. All right, so for number one, Mm, we're given a graph of a sinusoidal curve, and we want to figure out basically what the equation of it is supposed to be. Part A is to figure out the amplitude and the period, and then part B is to get those values for the actual equation. Amplitude you can just read off. That's the height from um, the center line of the sine curve to the extremities, so the peak or the trough. Either of them can go, and we're told that the tick marks are spaced 1 unit apart, so this amplitude is actually 5. Um, maybe I'll just use the panning hand so that I can actually see everything. So amplitude is 5. I wrote that there, and then period. So it's a bit funny because like you have these dashed lines that are pointed towards these troughs, which I've drawn in green. So you can then count how far apart they are and you'll get 12. But it's kind of misleading to use this because if you start to think about this as maybe being where the phase shift is for like part B, you actually get the wrong answer. So because I then found that out, I actually added a little bit to the notes. I added quite a few things to it today. Well, some things. So I added this little comment off to the side. Maybe I can make this larger. All right. So I added this comment saying like when you're doing this process of reading off information from the sinusoidal graph, what you are doing is you're picking a window from start to end, where when you just like cut that graph off from start to end, it should look like a sine packet. And I drew an example of a sine packet here. So this is the standard sine packet of from 0 to 2 pi. It's supposed to start at 0, go up, then go down, and then come back to 0. That's what a standard sine packet looks like. And so starting here at -1 is a no-go. It's not going to give you the right value. You have to start on these red ones, where it actually starts at 0 and then it goes up. So you could start here, you could start there. This one would really not make any sense at all to use. And I mean, it would make more sense to use this guy instead of this guy. So I use this one. That's why I put my phase shift as 2. Phase shift, again, is the starting place. The period is then n minus start. It's the length from here to there, where you get a whole sine packet. Okay. Right. So phase shift is 2. Good. And then the next thing for part B is then to compute all of those coefficients A, B, and C that get inserted into the graph. So you use these formulas. B is equal to 2 pi over P, the period, and C is equal to minus phi times B, phi being the phase shift. So I do that right there, 2 pi over P for B. So P is the period, so I do 2 pi over 12. That simplifies to pi over 6. For C, phase, it's minus phi times B. Phi is 2 minus 2. B is what we computed, pi over 6. So we get minus pi over 3. And then A, the amplitude, is 5. We can just have read it off. And then putting it all together. So this is like how you might want to then check your answer. So it's always nice to be able to find ways to check your answer just to make totally sure that you actually have the right answer. Is to actually graph this guy. So we have A, B, and C. We can insert them into the standard form of a sinusoidal function. And when we insert it, we get this equation. And then what you can do is graph this guy on a graphing calculator. So if you have a graphing calculator, you could do that, and then just set your window appropriately so that you can actually check whether whether what you see matches up with this graph that has been given to you. So when I first did this and then like checked the graph, I saw right away that using phase shift of -1 made no sense whatsoever, and then I realized why. So yeah, it's always great to be able to check your work to find ways to do so. Yeah, you should always do that. All right, number 2. So now this is the reverse. We're given the function and we want to sketch a graph. So we're going through this process from parts A through C. So the first thing is we want to get this thing into standard form. So the first thing about this is that what is standard form? Standard form is this format where A and B are both positive. And what you can see is that this is not in standard form to begin with. A is -2. So the fact that it's negative is an issue. We need to then transform our sinusoidal function into one that is in standard form. And in our notes, we have these things. So first of all, like, does the function involve cosine instead of sine? Well, in this case, no. So we can skip this part, and then we then fall into one of these 3 cases. And the case that we have in particular, we have just A being negative. So then our notes tell us that we are going to use this transformation. Minus sine of theta is equal to sine of theta plus pi. And I've actually written that down here to use this transformation. So this is what we're given, -2 sine of 4x minus pi over 3. And we want to convert it. Okay, how do we use this to convert? Well, the way that we think about what this formula is doing is it's taking negatives in front of sine. It's taking this negative in front of sine, the sine function, and it's absorbing it by then tacking a plus pi to the angle for the sine. So the idea is I can absorb negatives in front of sine by adding a plus pi in the angle portion of the function. Which is what happens here with this squiggly arrow. So the -2 becomes 2, the angle becomes the same angle, but then plus a pi to it. And then what we do after that is we simplify this a little bit. Pi minus pi over 3 becomes 2 pi over 3, and that is the answer for part A. For part B, find the amplitude, period, and phase shift. Well, amplitude we can just read off, that's the A, that's the value in front. Period and phase shift, we need the formulas. So let's look down here a little bit. Period is given by P equals 2 pi over B, which I've written there. B is this value 4, little b. In this case, it hasn't changed, but for other transformations, the B can change, I believe. Probably not that much. Probably just flips from minus to plus, or from negative to being positive. But yeah, just to be wary of that. And phase shift can really change, right? So phase shift is minus C over B, and here I've done the computation for it. So minus C is 2 pi over 3, minus C is, tack the negative on, and then B is 4 right there. So you end up getting this complex fraction, and then you can simplify it. So how I think of this is that this structure of a complex fraction, you can just squash the denominators together. But the way that you're probably more used to thinking about it is that this division by 4, you can rewrite as multiply by 1/4. So then you have multiply by 1/4, then you multiply across, and you get 3 times 4 in the denominator. So you end up with this guy, and then that simplifies to minus pi over 6. Okay, so that answers B. We got the amplitude, period, and phase shift. Part C, we now sketch this sinusoidal function over 2 periods. Okay, and, well, I've already done that, but let's talk through how you would start this off. So I've sort of I've sort of gone through the steps for doing this in the notes, except I have it over three periods. So you just remove one of the periods. I removed like the left one. So you start by drawing a number line, adding some tick marks. You want to start at your phase shift, your phi, and then you want to add p to that. So I did that calculation here. The phase shift is minus pi over 6. I add p to it, pi over 2. And then, well, pi over 2 is 3 pi over 6. 3 minus 1 gives you 2. So 2 pi over 6. And since we want another period, we add another period to this. So add another pi over 2, 3 pi over 6. 2 plus 3 is 5. So we got 5 pi over 6. So these are the other two tick marks. And of course, we reduce 2 pi over 6. We write it pi over 3. And then, well, for each of these subintervals, we then put a standard sign packet in to it. And then we draw the y-axis where it should belong. So we don't know necessarily that it's going to go here, but by looking at these values, we see, well, when does x equal 0? It's going to be between these two endpoints, and it's going to be closer to this minus pi over 6. I just sort of eyeballed it. And then, so you draw the vertical axis, and then you put tick marks at the heights of the sine curves. And this is a little bit too sketchy. It should kind of match up in height, but yeah, the two would be here, -2 would be there to just match the amplitude. Okay, and then that would be your sketch. Right. Oh, I really hope that the frame rate is not bad. Something is going wrong. Okay. All right. Overloaded again. Something is really being silly. Okay. For number 3, we have this trig equation, and well, this minus 1 over root 2, this value may not look so common to you, but that is actually just the value root 2 over 2, except rationalized in the other way. So if you rationalize the denominator for this, you get this guy. This is just the numerator rationalized version. So this is really just minus root 2 over 2. Okay, now how do you solve this trig equation? Well, what you should do is first ignore the sign. Think about this guy. Think about, when does cosine of some angle theta, when does cosine give you the value root 2 over 2 back? And this is going to require that you know your unit circle well enough. So, I mean, you could use like this really complicated thing. I would prefer to think about it in terms of this table. So the values for cosine, it's going to be, the outputs are here. And so you see root 2 over 2 shows up at for the angle pi over 4, which is a 45-degree angle. So the standard solution for this guy that you should think of, the simplest solution you should think of, is 45-degree angle pi over 4, right? But now we didn't account for the sign, the plus or minus. The fact that this is actually a minus here is important. So we know that our reference angle is going to be a 45-degree angle. The question is, when is cosine negative? Right, that's going to tell us which quadrants the angle actually is supposed to live in. And so we would draw our standard like graph with the cosine being x, sine being y. So cosine being negative tells us that the x coordinate needs to be negative, which tells us that it's supposed to be these two quadrants, the second and third quadrant. So we're talking about a 45-degree angle in the second and third quadrant. Now those have names, and those names are given in this second table in my unit circle notes. So 45-degree angle, second and third quadrant, you can just look them up, or you can just remember 1, 3, 5, 7 for 45-degree angle. So 3 and 5 are the names of the 45-degree angle in the second and third quadrants. And well, so those would be the solutions within one revolution of the unit circle. We want to find the solutions for this equation over the interval minus 2 pi to 3 pi. Okay, so, well, first let's think, what are the solutions in general? Like all the solutions of this equation without this interval restriction. Well, it would be 3 pi over 4 plus 2 pi k, where k is an integer. And also the solutions 5 pi over 4 plus 2 pi k, where k is an integer. Right? The plus 2 pi k is just multiple revolutions around the unit circle. So how we're going to work with this is we start with these infinite families, and then we are just kind of like trying to enumerate them. We're trying to list out those values until we escape this interval, until we leave this interval. And so the easy way to do this by hand would be to actually convert our values that we're working with so that we're doing arithmetic over the same denominator. So these are both over the denominator 4. I know I'm going to be adding multiple copies of 2 pi, adding or subtracting copies of 2 pi. So I'm rewriting 2 pi as 8 pi over 4, and I'm rewriting this interval so that the denominator is 4. So that's 12 pi over 4 and minus 8 pi over 4. And then we start out with the these standard representatives, right? The 3 pi over 4, 5 pi over 4, these are the standard guys that we would start with, and then we just add copies of 2 pi, or in this case, 8 pi over 4. So we add 8, 3 plus 8 is 11, and then if we add 8 one more time, we get 19. That escapes that's greater than 12. So we've left this interval. So we actually stop there for going to the right. Now going to the left, we subtract 2 pi. We subtract 8 pi over 4. Subtract 8. Right, so 3 minus 8 gives us negative 5. We're still within. We subtract 8 again, we get minus 13. We've left this interval. So we stop there. So these three values are the only values that are equivalent to the angle 3 pi over 4. Next, we then consider this other potential set of solutions that are equivalent to 5 pi over 4, and we do the same thing. We try going to the right as much as possible, try going to the left as much as possible. 5 pi over 4, if I add 8 to that, if I add 8 to 5, I get 13. We're greater than 12, so we've already left the interval. So we stop there. Subtracting 8 from 5, yeah, that's how you say it. 5 minus 8 is negative 3. And so, and minus 3 is still within bounds. But then if I subtract 8 again, I get minus 11, and I've left the interval. So we stop there. So our answer is this set of 5 values. These are the 5 values for x within this interval that solve this equation. These are the only values. Okay, and yeah, that's all I really want to say about that. For number 4, all right. So this is what is termed as a complicated or complex trig equation, solving this thing. So, well, first let's simplify it a little bit. Let's box this stuff together. Call this guy theta, and we've reduced our the equation we're considering to tangent of theta equals negative 1 over root 3, which is really quite similar in structure to the previous problems. Okay, so, well, now we're thinking, okay, when does tangent give me 1 over root 3? Let's ignore the sign first. So 1 over root 3, well, let's go to our unit circle. We see that tangent gives the output 1 over root 3 for the angle pi over 6, which is a 30-degree angle. So the reference angle that we are considering is pi over 6, or 30-degree angle. But notice we do have a negative here. So we are thinking about 30-degree angles in quadrants where tangent is negative. So when is tangent negative? Well, it's going to be the second and fourth quadrant. You can kind of remember this as being a checkerboard pattern. Tangent is it's positive here, positive in the third quadrant, and it's negative in the second and fourth. So 30-degree angle in the second and fourth quadrants, and we should give names to these angles. So you look at the unit circle again, and you see that for 30-degree angles, the names for these angles are 5 pi over 6 in the second quadrant and 11 pi over 6 in the fourth quadrant. So that's why we have 5 pi over 6, 11 pi over 6. Okay. And so these two are like representatives for the infinite families of solutions, right? You can then tack on a plus 2 pi k to both of these. But you can also do one other more slick thing, which is to realize that there's a symmetry that you can exploit here, right? If I go from the 5 pi over 6, I can rotate then by 180 degrees. I can add pi to that, and I'm going to end up at 11 pi over 6. If I then add another pi, another 180 degrees to it, I'm going to wind back at the value 5 pi over 6. Well, it'll be an angle equivalent to that. It'll be larger. 12 plus 12 pi over 6, so it'll be 17 pi over 6. But it's going to be equivalent to 5 pi over 6. It's going to land at the same point, but just be named differently. So, so because you can just add pi to go from one to the other and back, we can combine those two infinite families into one infinite family. We can write our set of solutions theta, as theta equals 5 pi over 6 plus pi k. So this ends up being an intermediate step, is finding the full set of solutions for this simplified trig equation, right? So the solution for this tangent theta equals minus 1 over root 3. All solutions are captured by this. Now we come back to the original problem we were working with. We do that by replacing the theta with how we've defined it. So we called this 2x plus pi over 3 inside the parentheses. We called that theta. So now we're just replacing this out, and we copy this down. So this is now what we're working with. And, well, what are we trying to find? We're trying to find all solutions, all values x that satisfy this equation. So, solve this equation for x. Subtract pi over 3. Do a bit of arithmetic to actually do that calculation. Don't really need to say anything about that, I think. You get pi over 2. And then divide this whole thing by 2 to get x, to isolate x. So pi over 2 divided by 2, you get pi over 4, and then this quantity divided by 2, you get pi over 2 times k. And then we bring back the condition that k is an integer, just to close things off completely. So this is the full set of solutions to this equation. Very good. All right. Right. For number 5, so this is another complex or complicated trig equation. How do we solve this guy? Well, what we should notice is that if we use the substitution y equals sine of x, we can actually rewrite this guy as a polynomial in terms of y. Like, we can view this thing as a polynomial in terms of sine x. Okay, and then, well, the whole point is that we have to solve this guy somehow. Well, how do we solve a quadratic? The general way is to use the quadratic formula. But here, this quadratic is actually nice. We can actually factor it. So how you would figure this out is, well, there's only one way to break 2. or to split 2 into factors, it's only 2 times 1. And so the ends are guaranteed to be that. So I would start with 2y and y, and then I know that 2 and 1 have to go somewhere, and I know there's going to be like a plus and minus. The goal is to make things add up to -3. Okay, and so you have to realize that it's going to be -4 plus 1 will give you -3. So you end up wanting to get a -4. That forces the -2 here to then multiply with the 2y, and then you get the 1 from 1 times y. So that will give you this middle term of -3. And then of course the end term, you can just check that it is -2. So this is the factorization of this quadratic. And well, now we replace y back with the original guy. So sine of x. So now I just replace y with sine of x. And so now what this equation is saying, right? We have some number times some number is equal to 0. Well, how is that going to happen? Well, it has to be that one of these numbers is 0. Maybe both of them are 0. That's also a possibility, but one of these guys has to be 0. So that splits our problem into cases. Either this first factor is equal to 0, or the second factor is equal to 0. And so then we consider those cases independent of one another, and we find solutions to these two different cases. And if we were to have found multiple, if the left-hand side and the right-hand side, if they both gave different sets of solutions, our final answer would be to union those sets of solutions, to just combine the sets by just sticking all the values together, tacking them all together. But what happens with the second side is that you get sine of x equals 2, and you should see that that's impossible, because you should know that sine is bounded above by 1, right? The graph of sine, it never exceeds the value 1, and it never goes below the value -1. And you can also visualize cosine as well. So sine and cosine both have this property. They're bounded above by 1, they're bounded below by -1. So you can't get sine of x equals 2. That's impossible. So this side yields 0 solutions. The left-hand side, though, has solutions. So I solve for sine of x, I can subtract 1, divide by 2. We get the equation sine of x equals -1/2. So we need to solve this trig equation now. Well, so ignoring this the plus minus, when does sine equal 1/2? Well, the angle that should come to mind is pi over 6, right? That's the value in the first quadrant. Sine obtains the value 1/2 for the angle pi over 6, which is the 30-degree angle. That's this there. Okay, and now let's bring back this consideration that the value we're actually looking for is -1/2, not +1/2. So we need it to be a 30-degree angle in quadrants where sine, the function sine, is negative. So drawing our axes, we see that sine is the y-axis. So we are looking at quadrants where the y-coordinate is negative in order to get sine to be negative. So we're thinking about the third and fourth quadrants. Okay, so it's the reference angle 30 degrees in the third and fourth quadrants. Looking over on our unit circle, 30-degree angle, third and fourth quadrants, we get 7 pi over 6 and 11 pi over 6. So that's why I've named these two solutions as such. And then the one final thing would be to well, we're looking for all solutions, okay? So these two values are just the solutions from 0 to 2 pi. To get all solutions, we then tack on a plus 2 pi k. And so that's why I've written my solutions in this format. 7 power of 6 plus 2 pi k, and also 11 power of 6 plus 2 pi k, where k is an integer. So this is the full set of solutions. Okay. Oh, encoding overloaded. Oh boy. All right. Okay. Number 6. So, all right. Find the geometric angle formed by these two vectors. Use exact values. So the geometric angle. This is newer material that we're going to be covering today, as of the time of recording this. Geometric angle, this formula is in this part of the notes. So the geometric angle between two things is given by this formula, arc cosine of the dot product of the two vectors divided by their magnitudes, or divided by the product of their magnitudes, perhaps. So what we need to compute is we need to calculate the two magnitudes and also the dot product, and then insert them into here and have things simplify so that we can actually figure out the arc cosine of the angle, or not the angle, the ratio of sides actually. This is a ratio of sides, right? The output should be an angle. Yeah. Okay. Right. So how do we compute magnitudes? Well, it's a distance formula. Magnitude is length of the vector. It's a distance formula. So what you do is you square the components, add them together, and then take a square root. So for v1, you have this minus root 3 squared plus 1 squared. So that gives you 3 plus 1, 4. Take the square root of 4, you get 2. For v2, 6 squared and 2 root 3 quantity squared. So you get 36 for the first guy. For the second guy, the algebra that you're supposed to know is that powers are going to distribute over multiplication and division. So you can rewrite this as 2 squared times square root of 3 squared. So the 2 squared is 4, and then root 3 squared is going to cancel. The square is going to cancel the square root, so you get 3. So this is then 48. Take the square root of 48. And then it's useful to actually be able to reduce this. So what you can realize is that 48 is 4 times 12, and 12 has another copy of 4 in it. So then you can repackage this as 16 times 3. And why is that useful? Well, because 16 is a square number. When we are reducing radicals like this, we want to actually pull out all the squares that we can find, all the square numbers we can find inside the number. We pull them out, and by pulling them out, we actually take the root, the square root here. So you see that when we pull 16 out of this number, we take its root, we get 4, and then the 3 stays inside the root. So square root of 48, when simplified, is 4 radical 3. Okay, so that is the or the magnitude of v2. And then the last thing I'm going to need in order to insert into this formula or expression is the dot product. So the dot product, if you're not used to it yet, I've written the formulas for dot product and skew product here. So v1 and v2 are these two things. This is kind of the standard convention. You have the x-coordinate, y-coordinate, and vector 1 has just subscripts of 1, vector 2 has subscripts of 2, and so the dot product is you just product the x's, product the y's, add them together. So here we product minus root 3 and 6, and add a product of 1 and 2 root 3, and then we do the simplification. So notice that both of these terms have root 3 in them. So I just rewrite it in a nicer format, and then imagine factoring out the root 3. Then you've got minus 6 plus 2. That's minus 4. So by factoring out the root 3, you see that it simplifies to this. This is like reverse distributing. Okay. So we got the dot product. Now we insert into the formula minus 4 root 3 divided by magnitude 1, magnitude 2, and you see that this 4 root 3 cancels there, and you're left with negative 1/2 inside arc cosine. Okay. So now we're thinking, what does this give back? One comment is that you could plug this into a calculator, but you might not recognize the value. So if you plug arc cosine of negative 1/2 into a calculator, you're going to get this decimal, and well, that may not be recognizable. You might then be clever enough to realize that all you need to do is divide by pi, and you end up getting a decimal that you should recognize. This 0.6 repeating is just 2/3. That's really annoying. Okay, so negative 2/3. Okay, or not negative, just 2/3. So you could maybe, playing around, you could recognize this. Do note that it says exact values. So if you wrote like this, it's not going to be acceptable. Right? It has to be exact. Okay. How would we think about this? So one thing I've drawn here in green is that this statement is kind of the same thing as saying what angle theta gives the well, we have that cosine of that angle equals negative 1/2, right? And so if you remember your unit circle, cosine is 1/2 for pi over 3 for 60-degree angles. To get negative 1/2, we need that the cosine is negative. So that's gonna be in the left quadrants, the quadrants 2 and 3. Okay, but now think about the fact. What do we know about arc cosine? Well, we know that its range doesn't go to this third quadrant. That's why I've shaded in blue these two quadrants. This is the range for arc cosine, which is something I've also added to my notes. I've added some stuff on the inverse trig functions. So we have that the range is from for arc cosine is from 0 to pi. So it's these top two quadrants. Okay, so arc cosine is going to give back this angle, an angle in the second quadrant that has reference angle being a 60-degree angle of pi over 3. So pi over 3 in the second quadrant. That's why I've written this. And well, knowing your unit circle, or otherwise, I guess, thinking about it, you can see that the 60-degree angle in the second quadrant is 2 pi over 3. Okay. And so that's how we get number 6, the geometric angle from these two vectors. Okay, good. Number 7, the dot product. We want to find the dot product of two vectors. We're given the magnitudes of the two vectors and also the magnitude of their sum. So when we see a problem with, when we see these kinds of givens and this thing, the thing you're supposed to think of is the generalized Pythagorean formulas, which I've written, I've added to my notes right here. So notice that the structure of it is kind of the same for this part, and then the only thing that really changes is that plus has plus, minus has minus in front of the 2 times the dot product. So it's kind of easy to actually remember this, I guess. But there you go, you have that. All right. So so because this involves the plus version, we have the plus 2 times the dot product. And then the way I've done the calculation is I've just used the given values, just inserted them in, so 9 squared, 3 squared, 7 squared, and then we solve for v1 dot v2. So 81 minus 9 minus 49, all divided by 2. And then I would chuck this into a calculator because I don't feel like thinking about it. You get 23 on top over 2. Okay. For 8, and I think this is the last problem, but there's 3 parts to it. So for 8, the first 2 are kind of similar to each other. They're inverse trig of a trig. The third one is different and kind of uses a different process. So when you have the trig evaluation on the inside, you should actually do the trig evaluation. When you have an inverse trig on the inside, you have to remember that an inverse trig is actually an angle, and you can figure it out as being like drawing the triangle that corresponds to that angle and then doing the trig, the subsequent trig evaluation on that triangle, reading it off from that triangle rather. Okay. But yeah, so A and B. So starting with A, arcsine of sine of 7 pi over 4. Right. So thinking about the evaluation of 7 pi over 4, well, pi over 4, the denominator being 4 tells me it's a 45-degree angle. I then need to ask myself what quadrant is it in, right? So the fact that it's a pi over 4, the fact that it's a 45-degree angle, that tells me that it's going to be plus or minus root 2 over 2. That's something we know from this table of values of like the trig functions evaluated at special angles. Okay, so cosine at pi over 4 is root 2 over 2. Or sine at pi over 4 is root 2 over 2. But then we need to consider the quadrant to figure out whether it's plus or minus. And we can think that 45-degree angle, it's 1357 for those values. You can look at it from this row in this second table. So 7 pi over 4 is actually a 45-degree angle in the fourth quadrant, which is why I've drawn it here. Okay, and I've labeled cosine and sine. So sine is the y coordinate, and see that for the fourth quadrant, it's negative. The y coordinate is negative. So the value is negative root 2 over 2. Okay, so far so good. Next, we think arcsine of negative root 2 over 2. Well, thinking about the range for arcsine, that's over here. Over here. The range for arcsine, minus pi over 2 to pi over 2, that's these two quadrants, the right quadrants that I've shaded. So the angle location doesn't change, but its name changes because 7 pi over 4 is outside of this interval. So we use a different name for this position. We instead call it minus pi over 4, right? These are conceptually different. This name, 7 pi over 4, has the connotation that we're going in the counterclockwise direction, whereas negative pi over 4 has the connotation that we're going in the clockwise direction. So, right. But they are equivalent to one another. Because you subtract 2 pi, you get from this, you get to this value. Or you add 2 pi to this, you get this value. Okay, so minus power of 4 is what the arcsine function will output. And then you can also see this, or you can double check this by just like plugging it into a calculator and just like checking that it indeed gives you the right value. So let's see, we're using radians, arcsine of negative root 2 over 2. You get that, and then if you do minus pi over 4, you see that you get the same decimal. So that's one way to double check your answer. Okay, for part B, arc cosine of 5 pi over 4. Okay, so first we want to evaluate this inner expression, this cosine of 5 pi over 4. Well, 5 pi over 4, 135. The over 4 means it's a 45-degree angle. So, okay, my computer is being a bit... Okay, yeah, so 45-degree angle, 135 tells me that it's a 45-degree angle in the third quadrant, which is why I drew it here. And cosine is therefore going to be minus root 2 over 2, right? 45-degree angle, you know the value is going to be root 2 over 2. And then the fact that we're in one of these left quadrants means that the cosine is negative, because cosine is the x-coordinate. Okay, right. But now arc cosine of this value. Well, the thing is, arc cosine has its range is 0 to pi. 0 to pi, remember that. So it's the top two quadrants. Well, so the third quadrant is not included there. So what happens is that we actually get an output with the same relative, or same reference angle. The reference angle is the same. It's still a 45-degree angle, but it's going to be in this quadrant, the second quadrant, instead of the third quadrant. So we've jumped quadrants. Which should make sense if you maybe think about the graph of it. So negative root 2 over 2, you see that we're going to land somewhere between the outputs are between pi over 2 and pi. So second quadrant. Okay. And so, yeah, the reference angle is a 45-degree angle. It's the 45-degree angle in the second quadrant. Going to unit circle, 45-degree angle in the second quadrant is 3 pi over 4, which is how you get this answer. Okay, so parts A and B, good. Part C, slightly different. Now we have the inverse trig function inside. And I did this in two different ways. So the first way is to think about it, and the second way is to resort to formulas. So, okay, if we think about it, arctan of negative 3 is going to be some angle. If we try to draw the triangle corresponding to this angle, well, the first thing is arctangent. Thinking about the outputs for arctangent, its outputs are minus pi over 2 to pi over 2. So it's the right quadrants, the first and fourth quadrants. The fact that the value we're plugging into arctan is negative tells us that the output is going to be in the fourth quadrant rather than the first. So we would draw our angle here, draw our reference triangle, dropping a perpendicular, putting our theta, and, well, knowing that this is arctangent, right? So tangent is going to be given by opposite over adjacent. We want opposite over adjacent to give me the value minus 3. So it's going to be, the minus should go on this side of the triangle, because this, you can see, like, in this quadrant, this side is viewed negatively because the y-axis is negative, whereas this side is viewed positively since the x-axis the x-coordinate is positive. Okay, and then we would get the last side, the hypotenuse, by doing Pythagorean theorem. So minus 3 quantity squared is 9, plus 1, 10, take the square root, you get root 10. And so this triangle corresponds, is the situation corresponding to this, this angle. Okay, and then from this triangle, we can read off what the value for sine at this angle should be. Sine is opposite over hypotenuse, so minus 3 over root 10, that gives me this. Okay, so that is one way to do this. The other way is to rely on the formulas. So where did I put those? Okay, there we go. Right, so sine of arctan of x. So if you're going to go about using the formulas, I recommend that you write the formula you're going to use down so that whoever grades it will know what you did. So sine of arctan is this formula here. So you write it down, and then you evaluate at x equals minus 3, and then you simplify it, because you should definitely do that. Okay, and so you get the same answer, which is good. All right, that's it.